All right, welcome everybody. Apologize again, my flight was canceled last minute, and the next flight I could get on wouldn't land until around 4 p.m., so it did nobody any good. So, excuse me. Thank you for joining me here. We'll just go through our course material here. So, I will still also be available at 2:30 on the link, the regular link that you would meet me on Tuesdays. I'll be there. If you have questions, you can pop in and ask those questions. But here we go. Let's start. We're on chapter 2.3, and this is the composition of functions. So suppose I had two functions. Let's say f of x is whatever it is. Let's say it's 2x squared plus 1, right? And let's say I had a second function g of x, and that is, let's say, 3x minus 2, right? Now, we talked about the algebra of functions, things you can do with f and g, like f plus g of x, f minus g of x, f over g of x, things like that. But we've also said, let's suppose we have this f of x, and I want to say f of w. Well, if I'm replacing x with w, then that w simply goes everywhere in that function that there's an x. So f of w is now 2 times w squared plus 1. But it's this w that we might get a little bit creative with, and instead of saying something simple like just changing it to f of w or evaluating the function itself at some point, f of 2 perhaps, and replacing the variable with a 2, we might input an entire function in there. So I might say, what happens if I take f at not just another variable, not just a number, but at some expression, let's say, oh, I don't know, 3x minus 2, right? Well, that is replacing the x term in the original function with 3x minus 2. So it's now 2 times 3x minus 2 squared plus 1. But this 3x minus 2 is g of x. And so we might see this written as f of g of x. Okay. This is the same thing. Because g of x is equal to 3x minus 2, I can write this as f of g of x. And so this is one notation for it. Another notation that we'll see is the composition. Whenever you see f and then an open circle like that, it's not an O, it's not a 0, it's just an open circle. But whenever you see that, f composition g is how that's read. And this is a brand new function, because a function evaluated at another function is still a function. And so that's what this means, and this is the notation we'll see. This right here is read as, let's see, I think I can add text. Yes, I can. F composed of g, or you might read it as f of g of x. So either one of those, that's how we read that. So let's take a look at some compositions. Let's say that we have f of x is given to us as, let's say, 2x plus 5. And let's say g of x is given to us as, I don't know, x squared plus 8. We can find f composition g of x. And this is the same thing as just taking f, evaluating it at g of x. So you can read it as f of g of x if you like. But that's just taking g of x, right? This x squared plus 8, and putting it into the, excuse me, putting it into the x of the f function. So that is 2 times, and instead of x, now the entire g function, x squared plus 8, and then plus 5 to finish off the f function. Or we can find g composed of f, or g of f of x. And that is taking g, which is x squared plus 8, but instead of the x, I'm going to input the 2x plus 5 in for the x term in the g function. So that is then now 2x plus 5 gets squared plus 8. We might also find something similar like f composed of f. F can compose of itself. It's a nested function. And so we would take 2x plus 5 and input it into itself into another 2x plus 5. So 2 times, instead of the x, I get 2x plus 5 plus 5. Similarly, g composed of g, or g of x, would be x squared plus 8 in for the x term of another x squared plus 8. And so we end up with that. Okay. Let's suppose now then we have f of x is given to us as x squared minus 3. And let's say g of x is given to us as 3x plus 1. Now, let's first find f composed of g of x. And that's again just taking g, plugging in to x in the f term, or in the f function. So that is 3x plus 1 gets squared, and then minus 3. Now we might also be able to input a different thing than just x, right? So I might have, say, evaluate f of g at a value. Let's say it's at 2. But I already know the function f of g of x, so I'm going to kind of cheat here and say this is just putting 2 into that. And so that is to say I've got 3 times 2 plus 1, that all gets squared, minus 3. And then I just go through the order of operations, make sure that I do the math right. Starting here, 3 times 2 is 6. So plus 1, and then squared, minus 3. 6 plus 1 is 7. So 7 squared minus 3. And so I get 49 minus 3 and 46. Now, another way to look at this is if I took f composed of g at 2, which is what we just did, this could be written as f of g of 2, right? That's another way to write this, and I can evaluate g of 2 and then figure out what that value comes down to and then plug in that into my f. So if I take a moment, let me scoot this over a little and figure out what g of 2 is. The g of 2 is just plugging a 2 in for g, so that's 3 times 2 plus 1. 3 times 2 is 6, plus 1 is 7. So g of 2 is 7, so that's the same thing as evaluating f at 7. But f evaluated at 7 is 7 squared minus 3. 7 squared is 49, and 49 minus 3 is 46. So there's 2 ways to look at this. You can look at the f of g as a new function and evaluate it at 2. Or you can evaluate g at 2, get 7, and then plug that in and evaluate f at 7. let's say we have f of x is the square root of x, and g of x is x minus 3. Now, we're asked here to find f composed of g, or f composition g, or f of g. All three of those are correct. And so I'm just going to take g and plug it into f. So that is now the square root of x minus 3. And then we're asked to find g composed of f of x. And that's just taking f and plugging it in for g. So that is the square root of x, and then minus 3 not in the square root. Right? And so we can see here that these two things are not equal. That's one thing that we might take away, that f of g is not the same of g of f. Right? Taking g and planting it into f is not the same thing as taking f and planting it into g. Okay? But we might also be asked, what are the domains of these, of f composed of g and g composed of f? What are those? Well, it's easy to see. The function here, x minus 3 under the square root, is restricted. It has to be greater than or equal to 0. And so we can treat this like a regular inequality and just solve it. So there's my domain. X has to be greater than or equal to 3, or if you like, in interval notation, bracket 3 to infinity, parenthesis. But that's not the same domain for this other g of f. The only issue I have here is that there's an x under the square root, and so that simply is x has to be greater than or equal to 0. And that's it. That's all I'm worried about, right? Or, sorry, and again, if you want 0 to infinity, yeah. All right, let's look at another example here. Let's say f of x is 1 over x minus 2, and g of x is 5 over x. Okay. Now these two functions carry with it an implied domain, well, not implied, they have domain issues. And so those domain issues are, for f of x, x can't be 2, which you'll see in the denominator, because if it is, 2 minus 2 is 0. In the denominator, you're dividing by 2, and the world blows up, right? But for the g of x, x can't be equal to 0, right? Now, let's find f of g of x, or f composed of g, whichever. And again, just for illustrative purposes, that is f evaluated at g of x, which is to say it's f evaluated at 5 over x, right? These are all equivalent representations, but that's just taking 5 over x, which is g of x, and plugging it into the x value here. And so I get 1 over 5 over x minus 2. Now we can simplify this, and I will. In the denominator, I'm going to call that 2 over 1, and then multiply it by top and bottom by x. And so this becomes still 1 over 5 over x minus 2x over x. In the denominator, I can combine these two fractions right here. So this becomes 1 over 5 minus 2x over x. But I've got this fraction in the denominator here. And I'll just flip this, and so this becomes then x over 5 minus 2x. Excuse me. Now the domain, where's my mouse? There we go. The domain of this is five minus 2x can't be equal to 0. Or 5 can't be equal to 2x by adding the 2x to the other side. And then, of course, dividing by 2 gives me my domain. X cannot be equal to 5 halves. Right? But that's not the only domain issue that I have, right? That's the domain issue of f of g after it's been simplified. But since I plugged g of x into this thing, g of x's domain issue carries in, because if x was equal to 0, I wouldn't have had a number to plug into here in the first place. And so I also have to consider that the input variable, or the input function, also has a domain that sticks. And so x can't be equal to 5 halves, but I also have to then say x cannot also be 0. Even though it's not evident by the result, I still have to consider that, because I would never have had a number to put into f if I had tried to evaluate g at 0. Even though plugging in 0 here, right, 0 here, 0 here would just be 0, it still doesn't work because of that input function that carries that domain issue all the way through. And so in the end, I have these two domain restrictions on f of g of x. We can do the same thing with g of f of x and see if it carries the same kind of restriction. So let's do, I'll start it over here, g composed of f of x is then going to be f, which is 1 over x minus 2, plugged in to the x part. So it's 5 over 1 over x minus 2, which this can flip and just multiply. So this becomes 5 multiplied by just x minus 2, right? And by all appearances, this is just a polynomial and there's no domain issues here. Or are there, right? Because again, if I take f of x, which was 1 over x minus 2, it carried with it a domain issued from the start that x couldn't be 2. So if I try to evaluate this at 2, right, I can. 2 minus 2 is 0, so this becomes 0 by all appearances of the composition function. But f carries that function, that domain issue with it, because I can't evaluate f at 2. I can't then say that there's a number to input into g at 2, right? And so are there domain issues? Yes, there are. That domain issue is that the primary function, the input function, has a domain issue, and that carries all the way through the problem. And then, of course, sorry, if you like, we can also write this in interval notation, so it would be negative infinity up to 2. We would exclude 2 and then union it back at 2 up to infinity. So this is just another way of writing the interval notation of that one single number 2 was taken out. All right, let's look at this. And I have h of x equals 2x minus 3 to the 5th. And let's say we have g of x. Oh, all right, my bad. And we want to find an f of x and a g of x such that h of x is f composed with g, right? And there's typically, when they ask you this question, there's an obvious one, but there's not ever really a perfectly exact one. And so what we would say is, well, since g is being input into f, it's easy to take this 2x minus 3 and call that g. And if it were input into something to get that 2x minus 3 raised to the 5th, then it's also easy to see, I think, that f of x, the outer function, is just that 5th power. And so we would say that it's x to the 5th, right? And you can double check it by doing the composition. F composed of g of x is taking 2x minus 3 and replacing the x. And so that is 2x minus 3 raised to the 5th. And we've done it. Right? So again, that is the most obvious one. There are other ones you could do. And there's a lot of, clever things that you could come up with here. But there is typically a pretty obvious one. Right. So let's look at this, 1 over x squared plus 3. I can come up with probably two. I could say f of x is 1 over x, and g of x is x squared plus 3, which would work if I take g of x, plug it in f of x, I get 1 over x squared plus 3. But I might also say, well, look at this. I can say f of x was 1 over x squared plus 3, or x plus 3, let's say. And let's say g of x was x squared. That would also work, right? If you really wanted to get, I don't know, pedantic probably is the word, I could say f of x is 1 over x squared plus 3, and g of x is x, because that also works, right? So they're not by any means unique. But again, that's probably the most obvious one. But if you're doing a test on paper and I'm grading it, any one of these is right, so they're all right. Yeah, that's it. That's it for 2.3. Let's dive into 2.4. And again, if you have questions on this, if you've watched this before the regular time for our class, I'll be online at 2:30 to talk to anybody that has questions. We can do more examples, anything like that. I'll also be online Tuesday during what would normally be our class. And if you have questions, again, you can talk to me then. That gives you a chance for after you've watched the videos to just come and ask questions. Okay, let's look at 2.4. So 2.4 now talks about symmetry. So symmetry is, let me see if I can remember how to snip. Yep, I can. There we go. How beautiful. So we've got this little butterfly, right? And symmetry is simply if I, in this butterfly's case, cut it in half, what is on the right-hand side looks like if you just folded it over and imprinted it on the left-hand side, then folded it back over, that looks more or less like what's happened here. There are imperfections because it's nature, but symmetry is simply that, is either, in this case, the right-hand side being a mirror image of the left-hand side, or in this case, we have two kinds of symmetry really going on here. I could draw that line vertical and say the left-hand side looks like the right-hand side, but I could also draw it here and say the top looks like it could be folded over to become the bottom. Moreover, though, and it's a little bit less so because there's this orange bit on the side here, but I could also say, well, I could have drawn it like that, folded over, and the top left part could have mirrored the bottom right, or just as easily I could have, well, my lines are terrible, but if I could draw a good line through the center there, the top right could also have folded over and become the bottom left. And that's what symmetry is. And so we have a couple of types of symmetry that we'll talk about. And the first one is symmetry about the x-axis. That's not helpful. There we go. And that looks like this. So here's our x-axis down here. And that x-axis is the line where if you look up, if you're standing on this axis, you look up and you see a point some distance away, you're going to be able to look down and see a point the same distance in the opposite direction. So here, if I stand at 3, I look up about 1 3/4. I'll look down and also see about 1 3/4. Right? Which is to say then that the ordered pair 4, 2, if that's on the graph and you have symmetry about the x-axis, you're going to have the point 4, -2. Right? And in fact, for any point, if you have some point x, y, and symmetry about the x-axis, then you also have the point x, comma, -y. And this is required for symmetry about the x-axis. We might also see, oh my gosh, move, symmetry about the y-axis, and that looks like this. Which, if we look at, I cut my y-axis off, but that's the y-axis right there. And if I cut it down there along the y-axis, the same story. If I'm standing, let's say right here, and I look to the right and I see a point, I can look to the left and see another point coinciding with that one, the same distance to the right and to the left, right? For example, if I'm standing right here on 4 on the y-axis, I look to the right and I see a point 3 spaces over, and I'll see one 3 spaces to the left as well. Which is to say, again, if you have symmetry about the y-axis and you have the point x, y on the graph, then you have the point -x, comma, y as well. That's not equal. That just means you have them both. And then we have another type, which is symmetry about the origin. And that looks like this. It's a little bit harder to see sometimes, but it looks like this. And that is to say, if I'm standing at the origin, there we go. If I'm standing right here and I look and I see a spot, right, then I should be able to look in the opposite direction and see a spot as well. Right? So if I look in this direction until I see that spot, I should be able to look in this direction and see that spot as well. Right? But they've got, let me clean this. We've got these points looking like it should require all 4 of them, but it doesn't really. The idea here is that if you have an X and a Y on your graph, then you'll have the opposite of both of those on the graph. So things that, let me find another one, because this can be a little bit confusing to look at this specific graph. Here's a good one as well. Let me just steal it. This is also symmetry about the origin, right? So it doesn't have to be all 4 quadrants have a point in common. It's just if you're standing here at this, in fact, this one here is not even a function. This one is a function, though. In fact, when you have symmetry about the origin, a lot of times you lose functions. But in this case, this is a function. And the idea is if I'm standing at the origin, if I look up until I see a spot, I just need to turn 180 degrees in the complete opposite direction, and I'll see another spot. So if I look over here and I see this spot here, then I should be able to look in the opposite direction and see that spot as well. Okay. So how do we test a function for symmetry? I'm just going to steal this so I don't have to write it all. This is straight out of the book. Right there. So, and essentially this is what I've written above. For the x, if you want to test for symmetry about the x-axis, if you replace y with negative y and you get the same equation out, then you have symmetry with respect to the x-axis. So before we move to the other ones, let's take a look at what that even means. So if I have something like, say, let's do this. So here's and it's not even a function, it's just an equation, right? Because this is actually not going to be a function. It won't pass your vertical line test. But in place of this y right here, if I replace that y with negative y, so now it's not just y squared, but it's negative y squared plus 2 equals x. And if I simplify this, negative y squared is negative y times negative y, which is the same thing as just a y squared. And so this simplifies to y squared plus 2 equals x. And that's the exact same thing that I had to start with. And so because of that, if it comes down to an equivalent equation by replacing y with negative y, which is what we just did, then this is symmetric with respect to the x-axis. Likewise, if I want to check for symmetry about the y-axis, I replace x with negative x. And if it becomes the same equation, then it is indeed symmetric about the y-axis. So one that is symmetric about the y-axis is y equals x squared, say plus 5. But again, I just want to replace the x with negative x, and I think it's essentially going to be the same thing that we just did here. The negative x that gets squared. The negative x squared becomes just x squared. And so it's the same. And so because I replaced x with negative x and got the same thing back, then this thing is indeed symmetric with respect to the y-axis. And then to replace, evaluate if something is symmetric about the origin, we're going to replace both x with negative x and y with negative y. And if it boils down to the same thing again, then it's symmetric with respect to the origin. And one that looks like that would be, let's do green perhaps to match, x squared plus y squared equals 1. If you know, this is a circle centered about the origin with a radius of 1, so it should work out. And I think I've kind of beaten into the dirt these x squareds. They're going to make your negatives go away. But you've got this negative x squared by replacing the x with negative x. Negative y squared. But again, these x squareds, well, negative x squared times negative, or sorry, negative x times negative x is just x squared. Negative y squared just becomes y squared equals 1. So replacing both, I got symmetry about the origin, right? So let's take a look at one and see if we have any type of symmetry. You might just simply be asked, test the equation x squared plus y to the 4th plus x equals 3 for symmetry. Which means you have to do all 3 tests, right? So first I'm going to replace, let's say, x with negative x, and that is negative x squared. And remember, when you replace the x here with the negative x, it has to go in parentheses because that whole thing needs to get squared. Plus y to the 4th plus x. Well, if I'm replacing it with minus x, it's now minus x equals 3. And this negative x squared will simplify down to x squared, but that's all I can do. And this is not the same as that. And so it's not symmetric about the y-axis. So we'll try the other one. Let's try y with negative y. And so that becomes x squared plus negative y to the 4th plus x equals 3. But this negative y to the 4th with that even power is going to simplify down to plus y to the 4th. And this is the same. So we have symmetry about the x-axis. And let's just try one more. It might be obvious at this point, but I'm going to take x into negative x, and then y I'm going to replace with negative y. And so that is negative x that gets squared plus negative y that gets squared minus x equals 3. And I think you can see this negatives, or this is to the 4th, not to this 2nd. Yeah. So the even powers here, that just becomes x squared plus y squared. But I get this minus x again, and that's not the same. And so there's no symmetry about the origin. Right. So we would then talk about things like even and odd. There are such things as even functions and odd functions. And let's just do this. An even function is an even function is a function with symmetry about the y-axis. And so that is to say, for an even function, we have this, that the function of x, f of x, is going to be the same thing as f of negative x, right? So if I replace negative x into the function, I get the same thing out. Not only do I know that I have symmetry about the y-axis, but I also know that it's a even function. And likewise, an odd function is has symmetry about the x-axis. Oh, I'm sorry. No, that's not right. It's about the origin. An odd function, because if you have symmetry about the x-axis, you're not even a function. But an odd function will have symmetry about the origin. And therefore, it follows that if you plug in f of negative x into, if you plug in negative x into the function itself, that should simplify down to the opposite of x, of f of x, right? So let's take a look. Oh, and there's one more classification. If neither of these two, these are the tests to see that and that. If neither of those two are result, then the function is neither. Right? And neither or not is just not the two cases above. So let's look at a couple and evaluate them. Let's look at f of x equals 5x to the 7th minus 4x to the 5th plus 2x. And then let's look at, say, g of x is 3x to the 4th minus 2x squared plus 1. Right? So I want to test both of these. So I'm going to plug in. The test is simply what happens when I plug in negative x. Right? If I get the same function back out, then it was this case. Right? If I plug in negative x into f and I get the same function back out, then this thing was even. But if I plug in negative x into f and I get the opposite of the function, or just a negative that's been drugged through the function, then it's odd. So we're going to see what happens in each of these. So f of negative x is 5 times negative x to the 7th minus 4 times negative x to the 5th, and then plus 2 times negative x. And again, with these odd powers, it should be pretty obvious. Odd powers are going to result in kind of an odd function. But this negative to the 7th power, that gets just pulled out, and this is negative 5x to the 7th. Right? A negative x to the 5th is going to end up being just negative of x to the 5th. So that turns into plus 4x to the 5th. And then, of course, minus 2x. But all of my signs have changed. Positive went to negative, negative went to positive, positive went to negative. So this is negative f of x. Excuse me. And so because it ended up being negative f of x, this is an odd function. So we'll do the same thing similarly over in g of x. Let's plug in g of negative x. This is 3 times negative x to the 4th minus 2 times negative x squared plus 1. And the 4th power, it's even power, so it's going to kind of kill that negative. So this is 3x to the 4th. Again, the negative x squared, the squared kills the negative, so that's still just negative 2x squared plus 1. But this is g of x. It's the same function that we started with, right? It's this whole thing. And because g of x then is equal to, sorry, g of negative x is equal to g of x, then this thing is indeed even. Try it here. In fact, I'm going to write this on the board, or on this board. Pause the video, give it a try, see if you can do it. Let's say that we have f of x equals 2x to the third minus 3x squared plus 4x plus 9. Pause it, try it, let me know if you think it's even, odd. Well, don't let me know because I'm not listening. I'm not real, I'm a video. But try it, and I'll do it now. So f of negative x is equal to 2 times negative x to the third minus 3 times negative x squared plus 4 times negative x plus 9. And on the odd part here, this negative in the odd power, that pulls out. So this is negative 2x to the third. On the even power, it doesn't because the squared kills it. So this is still minus 3x squared. And then is a single power, so it does come out. So that's minus 4x and plus 9. And this is neither the same function that we started with, but it's also not the opposite of it because not all of my signs changed, right? In front of the 2 is a positive, but it turns negative. In front of the 4 is a positive, but it turns negative. But in front of these other guys, in front of my 3x was negative and it stayed negative. In front of my 9 was positive and it stayed positive. So this guy is neither even or odd. Okay, that's it for what was that, 2.4. So anyway, hope this worked out for you. And again, I apologize about the flights. So let me know if you have issues. Let me know. And again, I'll be online at 2:30 Pacific time, and see anybody there that wants to be there. Thanks. Bye.